So, all right. So today we're going to talk about the multiplication rule. Multiplication rule applies when we have more than one event occurring, okay? So during a segment of Nightline, it was reported there's a 60% success rate of getting people to quit smoking if they undergo hypnosis. So 6 out of 10 people, on average, if they go through hypnosis, will successfully quit smoking, okay? So we want to find the probability that 8 randomly selected smokers who underwent all stop smoking. So what would need to happen if that were the case? Well, what we do is we take each event and we multiply those probabilities. So if I were trying to do that, I would say, well, what's the probability? Let's just say I randomly select one person. What is the probability that they quit smoking? For one person. 60%. That was given to us, okay? So this is person number 1. Now, to find the probability, say that I get 2 people who quit smoking, that if I select 2 people that both of them quit smoking, the probability of what I would do is I would multiply the 0.6 for each one of them. Now, we kind of talked about this first semester. Another way I could map this out, though it's going to be super annoying eventually, is I could say, hey, in a tree diagram, the first person either quits or they don't quit, right? And then the second person quits or they don't quit. And then the third person quits or doesn't quit. Is everybody with me? Okay, so this would be a way I could start mapping this out. Does everybody agree that doing this for 8 different people would be really, really obnoxious? Okay, so instead what we're going to do is we're just going to multiply and multiply and multiply. So if I want to find the probability that 3 out of 3 people quit smoking, I would do 0.6 times 0.6 for the first 2, times another 0.6 for the third person. Is everybody with me? Times another 0.6, then if I want to go all the way out to 8 people, I would need to do 0.6 for the 8th person. So in reality, I'm doing 0.6 8 times. And if you guys do this, you're going to find that this is a very, very small probability. Is everybody good? And I would not feel uncomfortable with this being a very small probability. All right, now, marble is selected from a bag that contains 4 red, 5 green, and 3 blue marbles. All right, so you guys, how many total marbles are there? 15. Just add them up, yeah? Okay. All right, so the marbles are replaced after each pick. What is the probability that 3 green marbles will be selected in a row? All right, so we're going to say, well, what is the probability that the first marble is green? 5 out of 15. Great. Times the probability the second marble is green. Well, if I'm replacing it, mixing it back up, it's going to keep being 5 out of 15. Now, how would this change if I'm grabbing marbles out of the bag, but instead of putting the green marble back, I'm just going to keep grabbing it? I'm going to grab the next one, okay? So, probability that the first one is green is 5 out of 15. Now, if I pull out a green marble, right? Because in order for all 3 to be green, the first one would have to be green, right? Okay? What is the probability that the second one would be green? Well, how many green do I have left? 4. Out of how many marbles do I have left? 14. And then what's the probability that the third one is green? 3 out of 13. And y'all, I found that to be 0.022. Okay, now, this brings up what we call a concept called independence. Two events are independent. Independent events, one event, the probability of an event occurring is not influenced by a previous event occurring. So, for example, for that first problem, I would call those two each time I pick a green marble, I would call it independent because the probability of the second marble being green doesn't change even if the first marble was or wasn't green. Is everybody with me? Okay. Dependent events, the probability of an event occurring is influenced by a previous occurring. If I'm not replacing that marble, the probability that the second one is green depends on if the first one was green or not. All right. So you're drawing 3 cards from a standard deck without replacement. What's the probability of all 3 cards being a heart? Okay. So, how many hearts are in a deck? 13, right? So it's the probability the first card's a heart? 13 out of 52. What's the probability the second one is a heart? In this case, it would be 12 out of 51. The third one would be 11 out of 50. How are we feeling, okay? And the very, very first thing I might do then for this one is say, we have a total of 29 people. Okay, we're randomly selecting 5 people to be part of a committee. If I'm selecting people to be part of a committee, am I replacing or not replacing?
Not replacing.
I'm not replacing, right? Because otherwise I can't pick the same person twice. So, what is the probability that the first person I select will be a woman? 16 out of 29, and then 15 out of 28. Is everybody with me on where these are coming from? Because I'm going down by 1 woman each time. And how many total fractions should I have if I'm selecting 5 people? 5 fractions. Okay. That answers the probability that every single person I select is a woman, right? So how could we figure out then the probability that we select at least one guy? So let's think this through for a second, okay? If I were to draw a tree diagram for this particular setting, selecting the first person that can either be, I need to make a little bit, you guys don't need to draw this out, I just need you to visualize what's going on here. The first person is either a woman or a man, yeah? And then I draw my next set of branches. All right, I'm not going to draw them all the way out. Okay, you guys, as I'm looking at this, are you with me that the branch of all women is this branch right here? What can we say about every other set of branches?
It has at least one man.
This one's got a man right here, this one's got a man right here, so on and so forth, okay? Is everybody with me? Okay, so in general, rule of thumb, and in fact, this rule is on your formula sheet, the probability of at least 1 is equivalent to 1 minus the probability of none. So, what is the probability of at least 1 man? It's 1 minus the probability of no men. What was the probability of no men? Well, no men would be equivalent to all women, yes? So 1 minus 0.037. How are we feeling? All right. 60% of landscapers are certified pesticide applicators. Guys, think about like the signs like True Green. When you walk through in the summertime, you'll see people with the little signs in their yard saying pesticides. So certified to do that particular skill using that particular chemical. All right. If 5 landscapers are randomly selected, what's the probability that none of them is certified to apply pesticides? What would you say? Let's see, in order for that to happen, the first person would not be able to apply pesticides. What's the probability the first guy I select can't apply the pesticides? 0.4? Yeah? Is everybody good? What about the next person? Also 0.4? So the probability of none would be 0.4 to the fifth. So the probability of at least one. It would round to 0.990. Okay. All right, lastly, we're going to talk through something called conditional probability. Let's say I'm going to draw a card from a shuffled deck. What is the probability that I draw a king, given that the first card is a heart? Okay? Now, here's my question. Okay? If I had to write out the fraction in words, how would we describe in words the fraction that'll answer this question? If I'm giving that the card is a heart, what does that tell me about my fraction? Well, so if I know the card is a heart, I'm drawing only out of the hearts. So it would be kings out of hearts. Yeah? But we got a slight problem with that. If I'm only drawing out of the hearts, am I doing all kings? If I know the card's a heart, you guys with me? If I know that the card is a heart, it's not all kings, it's kings and hearts. How many cards are a king and a heart? 1 out of how many cards that are hearts? 13. Okay? So this is what we call conditional probability. And for conditional probability, we use I think your formula sheet probably uses givens. We say the probability of A given B is how we might write that. Some symbol-wise, we might call that A with a vertical line B. Okay? And the way we find it is we say, well, what is the probability of A and B over the probability of B? You can almost feel like this B past the line is almost like that line's a fraction bar of this one over this one. Okay? All right, so let's look at an example. Use the table below to find the probability of getting into a car accident given that you are using your cell phone. So whenever I have a two-way table that doesn't have these, I like to add my totals. It makes a whole lot more sense to me. So this would be 21, this would be 10, this would be 4, this would be 27 for a total of 31 trials, and this described by this table. Okay? Now, given that somebody's using a cell phone, what is the probability that they get into a car accident? Well, if it's given the cell phone, I know I am in this column only. I only want to figure out how many people. So I want to do cell phone and accident over cell phone. Is everybody with me? Okay? Because if I'm given on their phone, I'm not talking about everybody. So my bottom number should be, who am I talking about? What do I know about these people? Everybody good? So in this case, I would call that 3 out of 21, which I'm sure is about 14%. About 0.143. I just throwing in my totals. All right, this next one. Use the table below to decide if male or female runners are more likely to run marathons. Okay, so What I want to find is, what is the probability of running a marathon given male? And the probability of running a marathon given female. So for the males, what would it be, y'all? 17 out of
25. Oh,
out of 27.
yeah, that's fine.
Females, it is 8 out of 12. Okay, now, in this case, if I were to ask you, are these two events independent? Can we say that the probability of running a marathon is influenced by your gender based off of this data? They're not the same. In fact, I could say women are more likely, based off of this table, women are more likely to run a marathon than men. Do we see it? Okay, so the events of gender and willingness to run a marathon are not independent based off of this particular set of data. Everybody good? Great, that's it. All right, so we still have 20 minutes. Guys,